Okay, this is Dr. Brothers, and this is the quiz number 2, Solutions. So, this morning in class we discussed a problem, and this is to clarify the discussion and to actually solve out this problem set. There were two main issues this morning. One, we didn't clarify the variables when we were doing the substitution. And two, there was a fundamental problem with the problem that I gave you guys. So it was not easy to solve. Actually, the problem statement that I gave this morning, it would have had imaginary solutions. So this problem, I've modified it to include parentheses around the negative n. So y sub n is equal to x of quantity negative n squared. And this should give us a solution set. Okay, so the first thing that we need to do, we're just going to look at this problem and gain a little bit of information about the actual problem. And then we'll look into whether it's linear, time invariant, and causal. So the first thing that we do, we're going to make a substitution so that we have a couple of different variables so we don't get things confused. So we're going to make a substitution. A substitution. So we're going to change out the variable in this equation. So we're going to say y sub m is equal to x of negative m squared. Sorry about that. Okay. Now, given this substitution, we should be able to keep things clear when we go and do the change, so we can see which way it's going. So the second thing we're going to do is we're going to assume a value for x. And this is x of n, not x of m. Alright, so we're going to say n, and the one that we had in class this morning was 0, 1, 2, 3, 4, and x of n was going to be equal to the quantities 1 3/4, 1/2, 1/4, and 0. So if we plot x of n, it's going to be value here, 3, let's see, 1 3/4, 1/2, 1/4, and then 0. And this is 0, 1, 2, 3, 4. Okay, so now we need to make a substitution into this n value in order to represent the output of the system. So what we're going to do is we've already created a separate variable. So we want to see what happens when we change the n time scale over to m. So we're going to say that n is equal to minus m squared. Where I went wrong in the lecture this morning, we didn't solve this out for m, because we have to substitute in the values that are here to find the new value of m. So you actually need to solve this equation to find out what the m values are going to be. So the first thing we have to do is take the square root of both sides. So the square root of n is equal to minus m, and then we have to take that negative sign over to the other side. So negative square root of n is equal to m. Okay. So the next thing that we need to do, now we have an equation that tells us, given an n value, which are the values up here, we can solve for our new value, which was made in this substitution in the first step. So now we can say m is equal to, and we plug the n value into the n in the equation. So the square root of 0 negated is still 0. And then 1 square root is 1 negation. So that's negative 1. And then the square root of 2 negative. I'm just going to write that out. I'll grab a calculator and solve that out in just a second and give an approximation. So, and then we have the negative square root of 3. Again, we're taking n and plugging it into the n value to solve for m. And then the last thing, the square root of 4 is 2, so negative 2. Alright, let me grab a calculator real fast, and I'll plug this in. Okay, so this is okay. 2 to the 0.5 is equal to, so to simplify these down, we have 0, then we have negative 1, and then we have negative 1.4, and then we have 3. We have negative 1.7, and we have negative 2. Okay, so now we have our new axes. So the step that we missed, the two main things that I missed this morning in lecture, we needed to make a variable substitution so that we can keep this n separated from this n. Once we did that, we make the n that's here, we're going to substitute in this guy into this original equation, and then solve out for what m is, because the m, this axis is n, and this is x of n, and then we're going to replot it for x of minus m squared on that axis, and this axis is going to be m. And so now we can see that we are here at 0. Oh, let me put this down. So now these values, we used 0 to determine what this is. So now this is x of quantity minus m squared, and quantity is equal to, and we can copy this row down because these are the values that we used to solve for here. So that's equal to 0, 1, sorry. This is why you don't do homework in pen. So let's try this again. X of minus m squared is equal to quantity 1 3/4, 1/2, 1/4, and 0, where the 2 corresponds to 0, the negative 1.7 corresponds to the 1/4, this one, and this one. Sorry, I made this all absolutely messy. So when we look at 0, the corresponding value is 1. We have a value right there. Then we go over here to negative 1, and that value is 3/4. And then we go to the negative 1.4. So this is negative 2, and 1.4 would be about here. That's the value of 1/2. And then we go to 1.7, and that's the 1/4. And then here, so you can see what this square did. It made them bunch up as they get out further and further. And then the negative was the time reversal. Again, working with the parentheses from the interior to the exterior. Okay, so that gives us a basic understanding of what this system does. You feed in points like this, it does a time reversal, and it also does a time scaling of a squared. So the larger and larger the values get, the more they're going to get bunched up in here. If we expanded this n-axis out, they would get bunched up even more because it's a square root operation that's working on n. Okay, so now, is this system linear? So, what we want to do is look at the system in terms of superposition. So if we take and say this is the output of the h function, if we have a system that we're calling h, y of m is this output. The input is this x of n. Okay, so we have x of n is going through some system h, and the output of this, which is y of n. And now I'm going to keep consistent units again. Jumping back and forth with this m and n is confusing, but this is something that we're going to have to get your head wrapped around. It's not easy. Okay, so we take this output and we run this down into a summation block, and this is going to be x of 1, y sub 1, and then we are going to have x of 2 of n that we run through an h block, and then the output of this again runs into the summation block, and this is going to be y sub 2 of n, and this is just y sub n. So if we trace this through, x1 goes through one h block and we get y1 of n. Well, okay, so we know what the equation for y is, and so we can just plug in x of quantity minus n squared x1 plus x2 of minus n squared is equal to y of n. Now what we want to look at is the other possibility. So the additive property says that you can take them and individually pass them through the system and sum them on the output in order to get y of n. The alternative that should be equal, and if it is equal it almost proves linearity, is if we sum these to begin with. So now if we take x1 of n and we're going to feed that through a summation block with x2 of n, those both go into a summation block. The output of that goes through the system h, and the output of this is y of n. And the question is, if this y of n, and we'll call this y of s, and we'll call this y of a, y of additive. Let's call this the sum and the additive. Alright, so now if we do this, we can see that this is x1 of n, x2 of n, summation. So at this point in time, this would be equal to x1 of n plus x2 of n, and h is going to act on all of that quantity passing through here in one instance. So we have to plug this in to this original equation that's up here. So this is where it gets tricky, because there's nothing in this original equation that specifies, is this a single equation or double equation or whatever. All we do is say whatever the input is, it's getting this time scaling. So to do this conversion, this h acting on this, we take all of the input in values and apply this, I keep pointing to the in, apply this in scaling. So we replace all of the input times the input ins with the shifted in scale. So this is going to be equal to x1 of minus n squared plus x2 of negative n squared is equal to y of a of n. So these two are the same. Therefore, it satisfies this property of superposition, and that's true. Let's try the other property of superposition. Okay, so the other property of superposition is that we can distribute the a through, meaning that if we take a multiplied by x of n and then apply it to h, this is going to be y of, let's call this y of m from y of multiplication. We're going to say that that is going to be equal to, and that's the test, if this is equal to x of n that is applied to the h, where the constant is then going to be multiplied by the output of the system to get y of, let's just go c. I'm doing terribly at labeling these values. So if this is true, though, this is the other property of superposition. Now, so we have x of n multiplied by a. So at this point in the line, this value is the input to the system, which is a, x of n, is having the system of h act on it. And that is going to be equal to y of m. So again, if we come back to the original equation, all this system is doing is messing with the time scale. And so we take this in and we replace it with the in that is adjusted by the system. So the a doesn't have anything done to it because it has no relation to time. So all this is a times x of quantity minus n squared in quantity is equal to y of m. And then we can look at this system where we've got h acting on x of n, and then we have that times a. This is equal to y of c. So again, we take this interior and we replace it with the time scale. And so this is a times x of the quantity minus n squared is equal to y of c. These two are identical. Therefore, it is linear because it passed both quantities. So we have the additive and we have the distributive, and so it is linear. Yes, linear. Alright, now the second thing, time invariant. Time invariant means that we can shift this to any place in the timeline and it will still have the same output value. So if we do a time delay by 5 clock ticks, it would be the same as if we had it at time 0. But we can see from this graph, at time 0, it leaves it alone. At time 1, it does a time reversal, and the spacing is still a value of 1. But then it starts to compact it as time moves forward. So time invariant means that as you move through the timeline, you can shift it anywhere you want, and it's still going to be the same thing. If we took this input and shifted it all the way over here to the right, took this and shifted it all the way over here to the right, it's going to give us the same looking output, just shifted in time. So one way that we can mathematically test for this is we can do the same type of substitution with the same values, except we can give an offset in n. And if that output comes out with the same axes, then it's time invariant. So we can look at this, though. We can look at these graphs and see that it is not time invariant. This graph is a linear output, and this has an exponential scaling, or a square root scaling, and so it is not time invariant. So I'm just going to write this as an explanation. It is not time invariant due to time scaling. Alright, now the third one is called causal. So this is, does it move forward in time? Are we always looking at something in the past? So given an input that goes higher and higher in time, are we looking at a value in the past, or are we going to look at a value in the future? So again, we can look at this graph, and we can see that as we move forward in time, this is our input, and this is our output. So if we look at time value of 1, that's at -1. That's in the past. Time value of 2 results in this time value. So we can see that as we move forward more in time, we actually look more backwards because of this time reversal, where we have the negative in here. So we are always looking at past values. So is it causal? Yes. And I'm again just going to write a sentence to explain why. So due to time reversal, the system is always looking at past values. Okay, now, just one word real quick about what we did in the original class this morning. So originally, we had said y sub n was equal to x of the quantity -n squared. Okay, so let's do this one out real quick and just see the plot of what it looks like, and see why I completely messed up when I gave you guys this problem, and it didn't work out at all. So we have, and my camera says I'm about to run out of time, so I'm actually going to stop this and start this as a new video.